Okay, welcome to video series 2 on probability and statistics in Python. And this is part 1 of the second video series in probability and statistics. In this particular video, we will be actually discussing the link between conditional probability and machine learning. So what is the basic and the modern advancements in machine learning? I will show you that they all have to do a great deal with conditional probability. So let's get started with conditional probability. Before moving on, it is important to realize the importance of conditional probability, particularly in the area of machine learning. As I mentioned earlier, this is the conditional probability that most machine learning basically uses this conditional probability in almost every model. Let me give you examples how machine learning basically uses this conditional probability. Before actually describing the use of conditional probability in machine learning, let me first tell you a little bit about random variables. Random variables. Don't worry about the very short time treatment of random variables in this particular video. We have a whole section on random variables. Actually, the next section of this course is about random variables, and we will treat the random variables at length. But just to introduce here, just to show you the importance of conditional probability in machine learning, I'm just introducing the random variables. Random variables are the variables that basically different values of those variables represent different events. Actually, that's a way to convert events to numbers. Once the events are converted to numbers, then you can try out whole statistics on events using these variables. Let me give you an example. Let's say you toss two coins simultaneously. Your sample space might be this: a head, or a head tails, or tails and head, or a tail. That's a sample space. Assume that all these outcomes are equally likely. Just assume that. And which means the probability of this outcome is 1 over 4, the probability of this outcome is 1 over 4, the probability of this outcome is 1 over 4, the probability of this outcome is 1 over 4. Now, we can set a random variable or the variable of our interest to be, let's say x is our random variable. X is a variable that represents number of heads in the above experiment. Now, what are the different values that x can take? Well, x can take value 0. In that case, if x take value 0, we are referring to this outcome, because this is the outcome or the event that contains this outcome only. X can take value 1. Well, in that case, if the number of heads is 1, then we are talking about an event that contains this particular outcome and that outcome. So event containing these two outcomes. Or x can take value 2, which means we are referring to an event that contains only this outcome. So rather than writing all different kind of events, we can just figure out the area or the variable of interest for us, and we can assign different numerical values to that variable, and each of that numerical value actually represents the underlying event. Now, rather than talking about the probabilities of different events, we can talk about the probability of these random variables. What's the probability that x will take value 0? Well, that is 1 over 4. What's the probability that x will take value 1? Because x can take value 1, and that actually goes to this event and that event. So the probability of this event is 2 over 4. So the probability that random variable will take value 1 will be 2 over 4. Now, what's the probability that x will take value 2? Because that refers to a singleton event will with just this one outcome. So that is again 1/4. Yeah. So for one particular experiment, you can have a lot of random variables. One random variable may be the number of heads. Another random variable may be the number of tails. That might be another random variable y. You can have another random variable z, which is maybe, I mean, you can define whatever variables of interest you have, but each random variable, oh, the variable is called random because when you perform an experiment, what value this x will take is random. We do not predict what the value will be there. So it can take the value 0, it can take the value 1, it can take the value 2, we do not know. So there is a randomness in prediction. So that's why they're like the experiment is called random, the same way the variable is called random, because we do not know what will happen. What can happen, we do not have certainty for that. We will treat these random variables in detail, in full length in our next section. But here I have just introduced this to show you the power of conditional probability in machine learning. Now consider, for example, there is an experiment, and the experiment is that different people come in to a door. Let's say that's your office door. That's your office door. Okay, and there's a camera on top of that. There's a camera on top of that door, and people come here, and the door lock opens automatically if this particular person is authorized to come in or not. That application is basically that can be achieved through a face recognition application. Face recognition application. Now consider in this particular office or whatever area that is, consider only 10 people are allowed that are employees of this office or authorized or whatever. And let's say these 10 people, let's say y is a random variable that represents the identity of any person. Y is a random variable representing identity of a person that walks into the office. Because we have mentioned there are only 10 different people that are there, so the values that y can take belongs to this particular set, 1, 2, 3, 10. Let's say ID 1 means person 1, ID 2 means person 2, ID 3 means person 3, and so on. This variable is random because next time which person will walk in, we do not know that for sure. Further, assume x is a random variable that represents the face image. Later in this course, we will see this x not only a one variable, it is actually a random vector which has a lot of variables inside. But just for now, assume that this is a face image. By face, an image is simply a matrix of a lot of numbers with different patterns. What these intensity values are, let's say that is represented by x. Now, let's say we want to find out the probability that the person that is just enters now, whose image we have, let's say we have taken the image from the camera and that image value is this I. Let's say we have taken that. The camera just gives us the image and we know what are the values of x. Given the image, what is the probability? We want to find out the probability that this particular person is person 1. We need to find out that probability. So that probability, eventually, if we are able to find out that probability, that might be 0.2. We then try to find out the likelihood that the person eventually actually is the person 2. And that probability might turn out to be 0.7. And so on. I mean, and then we will pick the probability that is based on the maximum probability, and we will say, okay, this is that particular person. But see here, the whole face recognition app that relies on conditional probability you need to find out the probability of this y given the image. Similarly, if you want to find out the, for example, activity recognition, you have a video. Video is just a sequence of a lot of images. You have a video, and you need to find out in this particular video what activity is being performed. Then y will be a random variable that actually codes all different kind of activities, and x will be a random variable that will represent the video or the video data, sometimes called the features that we will see in detail in the next section. So now again, your goal is to model this probability distribution, which is again a conditional probability. So and then if you want a text to speech converter, you again have this conditional probability. In the regression problems where you want to estimate a particular kind of continuous data, for example, you need to find out the temperature given the conditions. Let's say somebody give you a lot of conditions that humidity level is this much and air pressure is this much. What do you think? What will be the temperature? If you want to predict the temperature given the rest of the variables, you can do that again. You can model that problem again as a conditional probability modeling. So although I was too fast here in this particular video, I have explained certain concepts that we will be dealing with in our future videos of the same course. But I just wanted to mention that this conditional probability that actually is extremely powerful, and classification and regression, all these kind of problems, they actually model this kind of probability law, and this kind of probability law is basically conditional probability, and that's a conditional probability whether you're working in regression or you are working in classification. At the end of the day, you are modeling this probability law. And guess what? Whether you are modeling that probability law using classical techniques like support vector machines or logistic regressions or maybe random forests or ensemble classifier, or even if you're using deep neural networks, at the end of the day, you're modeling this probability law. Although when we are dealing with these kind of deep neural networks and support vector machines, or for example, when we are dealing with logistic regression models and stuff like so, maybe we hide these kind of details, and maybe we do not realize that actually at the end of the day we are modeling a conditional probability distribution. But at the end of the day, whatever we achieved, we actually train a conditional probability law. And all the machine learning training where a neural network is being trained, random forest is being trained, a logistic regression is being trained, support vector machine. Let me change the word support vector machine to relevance vector machines, because the relevance vector machines, they have more connection to probabilistic modeling rather than support vector machines, because the support vector machines extension to multiple classes is not that straightforward in probabilistic sense. However, in relevance vector machines, which is a form of support vector machine in different assumptions, that has a probabilistic modeling and multi-class extension, and that also models again the conditional probability. So if you have heard about an application YOLO, you only look once, if you have heard about that application that models a conditional probability, if you have heard about text to speech recognition system that models a conditional probability, if you have heard about activity recognition that actually models a conditional probability, almost all the applications dealing with regression and classification, they actually have to model the conditional probability one way or the other. So I mean, although one can just go to the universe of machine learning and deep learning without realizing the fact that the underlying all the training process is basically building a conditional probability model. Without realizing that, you can just go into the machine learning universe. But it is always good to know that the roots of all these concepts, they are back in probability and statistics. So yeah, so I mean, I have used a lot of terms in this particular video, and I'm not expecting you to know all these terms already. I just wanted to mention that whatever you are going through, that is not just useless. I mean, these are the roots of all modern machine learning, probability theory, and particularly this conditional probability. We will unfold all these concepts that are explained in this video in the subsequent videos and sections. But I just wanted to introduce you the power and the applications of these concepts. These are not just I mean, the concepts are not just about rolling a die or tossing a coin. This is not just about that. Although we teach the concepts using very simple examples, but the application of concepts, they are everywhere. Everywhere in machine learning, everywhere. So, as I said, I'm not expecting any one of you to know the terms that I've spoken. For example, I've spoken a lot of terms like random vector, feature vector. I might have spoken the term support vector machine, relevance vector machine, logistic regression, deep neural networks. I've spoken these kind of terms. These are all the terms that are very common in machine learning. And I do not expect you to know all these terms right now. And that's okay, I know that. But I wanted to connect the conditional probability to these terms, because all these kind of classification and regression, oh, by the way, I have used the term classification and regression as well. They are also machine learning terms. But I just wanted to mention that these are basically the hot topics on machine learning. All these topics are hot topics. So deep neural network is really a hot topic in machine learning these days. And whether you are solving a classification problem or a regression problem using a deep neural network, you are modeling a conditional probability distribution. How amazing is that? I mean, the roots of all these kind of modern techniques in data science, they go back to probability theory. And that was the primary reason to introduce these terms right now, because you might be getting bored of why we are using the examples of a die every time, why we are tossing a coin, what we have to do with the coin, what are the real life problems in which the coin is tossed and they are interesting problems. Well, I'm using very simple examples to teach you the concepts that actually target very complicated situations. So don't worry about the coin and the dice. These are just to introduce you the concepts in easy ways, but do not think that the concept just stay with coins and dice. They go beyond and they go everywhere. Yeah, so don't worry, we will unravel these terms, particularly the regression terms and classification terms, estimations, and by the way, let me introduce one more thing in this video that might be getting messier and messier, this particular video. Let me introduce one more thing. Modeling this probability distribution, probability law, requires statistics. So for now, you might be thinking till now, where is the statistics? We are just I mean, working with probability of this event, probability of that event, and that kind of stuff. Where is the statistics? Well, modeling of this particular probability distribution requires to come up with the patterns from the historical data, sometimes called the training data, and all those techniques, they require statistics, the understanding of data, to come up with this particular probability law for predictions. So yeah, I mean, these things are interlinked. They are really interlinked. So yeah, hold on. Very interesting things are coming. Hope to see you in the next video. In this video, we discussed basically the link between conditional probability and machine learning. In the next video, in part 2 of the same series, We will be discussing some random variables. Basically, we will be discussing the random variables that can be encountered in real data sets. So I'll be showing you the random variables and working with random variables in real data sets. What are the random variables? What's the notion of random variables in real data sets in data science? So hope to see you in the next part of this video series. Okay, welcome to part 2 of video series 2 for mastering probability and statistics in Python. In the previous part of the video series, we discussed basically the link of conditional probability and machine learning. In this part, we are going to discuss the random variables in the real data sets. So we will explore some of maybe a couple of real data sets in Python, and I will show you the notion of random variables that are there and how to identify the random variables and what to do, what not to do with the random variables to build data science models in real data sets. So let's dive into the random variables for real data sets. We have discussed these random variables a lot, particularly discrete random variables, the random variables that has countable values. I can discuss theory more. I can discuss more about random variables, discrete random variables, a lot of derivations, a lot of examples and stuff. But I just feel feasible or necessary just to show you some real data sets and build a connection of these random variables on real data sets. And particularly what kind of random variables are there in real data sets, particularly in data science and machine learning, what kind of data sets are there? What are the notions of random variables are there in the data sets, and what we really do in those kind of data sets. So let's go to Python and see some of the built-in data sets and get a look and feel of what random variable is in real data sets and what are the tasks that are associated with, what are the machine learning tasks and what those tasks have to do with these concepts that we just studied so far. So let's go to the let's go back to Jupyter Notebook. So let's import pandas as PD, the dataset library for handling different kind of data sets. Let's import, for example, we already have SNS with us, so let's import some data. Let's say let's import iris data. So iris data from SNS dot load dataset iris. Let's import that data and see what that data looks like. So let's just see the first 5 records. Here you can see the data has different kind of attributes. We can call them attributes. So we can call them attributes like this. Sepal length is an attribute, sepal width is an attribute, petal length is an attribute, petal width is an attribute, and the category is this attribute species. The different kind of categories, let's see the different kind of categories. So let's say iris dot species dot unique. So the different kind of so there are 3 different kind of categories: setosa, versicular, and virginica. These are 3 different. So the total number of different values for this particular attribute is 3 values. This particular attribute is continuous. It can have several values. I mean 5.1, 5.1223 or something like so. This is sepal width and all that stuff. In machine learning, we call these attributes as attributes or features, but these are really the random variables. One random variable is sepal length, one random variable is sepal width, one random variable is petal length, one random variable is petal width, and one random variable is the type species. For example, if the next person walks in, and let's say we have certain machinery or extractors that can measure sepal lengths and sepal widths. Let's say we have tool or machinery that can that machinery can measure these kind of attributes: sepal length, sepal width, petal length, petal width, and let's say we can define the species as well. There is a machinery that can specify that as well. Let's say the new person that will come in, what will be the sepal length of that person? Well, that's random. It can be any number. What will be the sepal width? That's again random. What will be the petal length? Random. What will be the petal width? Random. What will be the category of that person? We do not know. So all these are random variables. And one goal might be to come up with a distribution that says, okay, what's the distribution? What's the probability of species? What's the probability that species is setosa given the values of random variables? For example, let me call the sepal length as random variable x1 that has certain value. Let me call the random variable x2 as the sepal width. Let's say that has a certain value. X3 is, let's say, petal length that has a certain value. X4 is, let's say, the petal width. That's a random variable that has a value. So we might be interested in this particular distribution. If we, for example, specify the random variable species as y, we really are interested in the probability mass function of y given these four random variables. And we are calling this as probability mass function because the total number of values that this y can take are just 3. Y can take values between, let's say setosa is coded as 0, versicular that is coded as 1, let's say virginica, let's say that is coded as 2. So the total different values that this y can take, setosa has a code 0, let's say, as we can see here, setosa, versicular, and virginica, they have different codes. Let's give them different codes 0, 1, and 2. So this is basically the probability mass function because y is discrete. But what about these x1, x2, x3, x4? Are they discrete? What about the joint distribution? I mean, x1 is maybe a completely different random variable with different distribution. This x2 is a random variable maybe with different distribution. x3 is a random variable individually with this different distribution. x4 is a random variable with a completely different distribution. What about when they play together? Their joint distribution. What do we mean by joint distribution? What we have to do with multiple random variables? We need to know that. But at the end of the day, if somehow, one way or the other, if somehow we can specify this PMF, this probability mass function, then if this probability mass function is specified somehow, maybe going through data, maybe applying certain statistics of the data that we will see in detail in the upcoming videos. But right now, I just want to give you a look and feel that this is a real data. These are random variables, and we are interested in this particular distribution. Where this is a random variable, that's a random variable, that's a random variable, that's a random variable. And we are interested in if you want to do this classification, if you want to, for example, if our goal is that given the sepal length, and given the sepal width, given the petal length, given the petal width, can we determine the category? Can we determine the species? Maybe we have machinery or sometimes called a feature extractor that can extract these kind of values automatically. Then our goal is, given these values, can we detect species? Well, that problem is exactly this. Can we model this PMF? If we can model this PMF from the data or using certain tools, at the end of the day, if we can model this PMF, where x1 is a random variable representing the sepal length, this is sepal width, this is petal length, petal width. If we can model this distribution, the PMF, then we have our problem solved, and that is a classification problem. But here you can see these random variables, sepal length, sepal width, petal length, petal width. they don't look like to be discrete. For example, sepal length might be 5.1, it might be 5.001, it might be 5.111332224. And sepal length can assume any value, for example, between 4.9 and 5.1. Any value in between might be a valid value. So it is no longer discrete. The total number of values that a sepal length can assume is not countable. These are continuous. And there are so many continuous, all these are continuous. There may be a mix of continuous and discrete values. For example, let's load another data set. For example, a Titanic data set. T is sns.load data set, let's say Titanic. If you see that data set, for example, there may be a mixture of values. Here, one random variable is survived. That's a Bernoulli random variable, because here, whether a person survives or not, so the values are 0 and 1. That's a Bernoulli random variable. If you want to see t dot survived dot unique, so if you see that the only unique values are 0 and 1. So this random variable, whether the next person will survive or not, that's a Bernoulli random variable. Then there are passenger class. This p class, that might be, let's see, t dot p class dot unique. That might be, that's again a discrete random variable with just 3 values. This gender, that's a discrete random variable. Age, that I guess is a discrete random variable. Siblings, that's a discrete random variable. Parts, that it's a discrete random variable. So several random variables are discrete, but here this fair doesn't look like a discrete random variable. It looks like a continuous random variable. Then we can have a mixture of discrete and continuous random variables, and if our goal is to predict the survival given the rest, so if that is our variable of interest, which is Bernoulli, and we want to basically predict the survival rate given the rest of the values, given the rest of the random variables. That is basically a classification problem. And in this particular paradigm, it looks like if y is if y, for example, if y represents the survival, then our goal is to build a PMF or probability model of y given x1, x2, x3, x4, x5, and so on. And these are several random variables. And some of them are discrete, some of them are continuous. How we are going to model a PMF with a mixture of discrete and continuous random variables, and more precisely, there are multiple random variables. Each one individually can have a different probability distribution. And first of all, what is the way to define distribution for a continuous random variable? We have to see that. Then we might be able to mix the discrete random variable with continuous random variables and stuff like so. So again, at the end of the day, if we want to solve the classification problem for this, for example, Titanic data set, we have to model this probability distribution, which is a conditional probability distribution. We have to model that somehow from data using certain techniques that we will learn in the upcoming videos as well. But I'm just giving you a look and feel of what random variables they look like. And it is not always required to have a very good description of what a random variable is. Sometimes the real data just arrives and we are just interested in a one random variable, whatever its description is, based on the rest of the random variables. We need not to know, these names need not to be very descriptive and telling what the numbers where they came from and stuff like so. Sometimes the data might just be written in these names that may be very unfamiliar to you. And then, but your goal is to go through the data, somehow come up with a probability distribution, which sometimes we call as let the data talk. Data will define, data will drive all the distribution and all that stuff. So for example, let me give you an example. Let me give you an example of another file data set that is located there. Let's say I have this data file here. Yeah, so that's a bias correction data set. Let me just copy the path of it. Control C. Let me just open up and see if we can read that file. pd.read CSV, or let's see if we can read it properly. b.shape. Yeah, we read it. So now if you see b.head, so here you have a lot of random variables: station, date, present temperature max, that's a temperature data, present temperature minimum, that is LD, APS, RH min, whatever that means, it has these values. I need not to know what this represent. If I know, that might be better, but even if I don't know, I will see the data and come up with the distribution. That all I know is this is some random variable, and I have to deal with it. That's another random variable. There are so many random variables here, actually 25 of those. And what if I'm interested in given all these, given the values of all these random variables, what if I'm interested in, given all the random variables, I want to predict the maximum temperature for the next day and the minimum temperature for the next day. So given a lot of features, the values of a lot of random variables, I want to predict the maximum temperature for the next day and maximum temperature for minimum temperature for the next day. Here you see what you want to predict is also continuous. It is no longer discrete. So which means if you go back to your page again, which means you're going to build a probability model. You want to predict the probability. You want to build a probability model for y, where y may be the next temperature, the temperature of the next day, maximum temperature of the next day, given a lot of information, given the values of a lot of other random variables. But here, this y is no longer discrete, so you cannot call this probability model as a PMF, because PMF is referred to the probability model or probability mass function for discrete random variables. If this y is no longer discrete, how can we model the distribution of that? And it can appear, I mean, in classification problems, for example, this particular variable is always discrete, so it is okay to just go with PMF. But in regression problems where we want to predict a continuous value, which may not assume countable values, this random variable will not be discrete, and how to handle these non-discrete variables. This is not just theoretical part. I mean, in all regression problems, the variable of interest, sometimes called the dependent variable or the dependent feature on the rest, that is no longer discrete. So how to model this distribution? And by the way, if we want to predict the value, the regression value, the value of this variable, should we go for the probability distribution for that, and check what's the probability that y will take value 1, what's the probability that y will take value 1.31, and so on. Should we list all the probability values and pick the maximum one? Is that true? Or should we do something else? Maybe we calculate the expected value of x, or average that y can take given these situations. Yeah, I mean, there are a lot of things. We have just covered Bernoulli, I mean, geometric, binomial, and stuff like so. And you might be thinking that where they play the role. Well, the real data set, when you see it, all the attributes, whether you are doing a classification problem or a regression problem in machine learning, you are given the values of a lot of random variables, and you are going to predict a particular random variable for that. And you have to build a probability model from the data. So this data, the data is given to you, sometimes called the training data, and using that data, somehow you have to build this model. And building this model from data is not an easy task. It's a really tricky task, and sometimes really hard. And that's what you want to do. So you need to know the random variables. What are these? Sometimes some of the values of the random variables, they are given and you're interested in the rest. Consider, for example, again, that I also mentioned, if in the face recognition problem, these random variables, they might be the intensity values of individual grid pixels, and this might be the identity of the person. Now, if the camera captures the image, the face image, then these values will be available because the camera supplies these values. But the camera doesn't know, I mean, nobody knows, given these values, what should be the identity of the person. That you have to predict. So in many cases, these feature extractors, they are available, and they supply the values that you need, that you want to condition on. But then the real goal is to predict this value. And to predict this value, you have to build a probability model. And to build a probability model, you need to go through a lot of data to build that model reliably. Yeah. So in this particular video, I built a lot of needs that are required. Number one, how to handle a continuous random variable. What if the random variable does not assume countable values? How to handle that? Number one, that's a problem. We have to see it. We don't know yet how to deal with that. Number two, what if there are more than one random variables with different distributions? Their individual distributions may be different, but what if they work in a joint fashion? So how to model joint distribution of several random variables, more than one random variables? Well, this joint distribution also have two cases. If all the random variables, they are continuous, and all of them, they are discrete. So we have to see that. And the third confusion is, what if there are, the third thing that we have to see is, what if these several random variables, they are mixed types. Some of them are discrete, some of them are continuous. Because at the end of the day, we are going to read the real data. The real data will be full of several continuous random variables, several discrete random variables. It might be a classification problem in which the target random variable will be discrete. It might be a regression problem in which the target random variable might be continuous also. So how to model joint distributions, how to model conditional distributions, given several random variables, how to model joint distributions, how to apply a Bayes rule in this kind of situation when we have a lot of random variables, not just one. Yeah, so we have to answer all these questions to actually get juice of the data, to get the actual training from the data, to get the actual model from the data. So yeah, we have to go through continuous distributions, continuous random variables. We have to go through multiple random variables. We have to build the joint distribution or the joint probability models that involve multiple random variables, mixed random variables. And then we will be able to go and look into the data, and we'll be able to build those models using statistics. Yeah, so we have to do that. So a lot of things are coming. Hope to see you in the next video. In this video, we discussed the random variables in real data sets by actually showing you the random variables on a couple of data sets in Python. In the next video, part 3 of the same series, we are going to discuss a continuous random variable, particularly the Gaussian random variable. And we will be discussing that random variable, we'll be plotting that random variable, we will be seeing its parameters and what is the impact of the parameter over the continuous density of the Gaussian random variable. So hope to see you in the next part. Okay, welcome to the third part of the video series 2 of Mastering Probability and Statistics in Python. In this particular part, we will be discussing continuous random variables, particularly the Gaussian random variable. And we will be playing with the Gaussian random variable in Python, we will be also looking into iris data set, the real data set that is there in Python. We will be looking into the distribution of different random variables there, and we will be seeing whether different random variables, they can be modeled using Gaussian random variable or not. So yeah, let's dive in. Okay, let's play with this Gaussian random variable. Last time we saw this exponential random variable. Let's see the Gaussian random variable in this particular video. So let's generate some data. np dot linspace. Let's start from, let's say, minus 10 to, let's say, go to, let's say, 10, or maybe minus, let's say, 20. Minus 20, you start from minus 20, go to 20 and generate, let's say, 10,000 points, let's say. So then fx, first of all, we have to define mu. Let's say the mu is 1, and sigma, let's say sigma is also 1 for now, let's say. And so fx will be np dot exponential, and that is minus x minus mu square. So that's it. That's the then we divide that by 2 sigma square, so 2 steric sigma square. So yeah, let me put the brackets so that we do not mess things up. Yeah, so that is exponential with this bracket match with this one, this bracket match with this one, this bracket match with this one. So I think everything is fine. So that's the exponential value divided by the normalization factor, which is 2 steric np dot pi steric sigma square, and we take a square root of all these things. So this we take square root of that. So that's our function if there is no problem in the bracketing and matching and all that stuff, I guess. So yeah, so that's fx. Let's see if it works. I guess yes. So now let's plot this. plt dot plot x fx and see what happens. Yeah, so here you can see that's the distribution. It starts from minus 10 and 10 and goes all the way up to this, and the distribution is, it looks like that the distribution is centered here, which is mu, and our mu here was 1 and the sigma is 1. Let's play with this by changing the values of this mu and sigma. Let's keep the sigma fixed and let's change the mu and see what happens. So let's see. So for example, all the mu's, let's see, all the mu's are np dot range, let's say starting from 1, let's say ending at, let's say maybe 20, and take the jump of 2. These are all the mu's. Let's say for mu in mu's, do this stuff. So do that, and let's copy this code here to here so that we just plot the things right away. Control V. Yeah. So let's see what happens. Yeah. So as you can expect, These are all different Gaussians. So changing the mu just shifts the Gaussian distribution to the new mu, and all these are the distributions. Let's see the impact of. By the way, if we take the step, if we take the step, for example, let's go from minus 20 to 20 with the jump of, let's say, 10. Take the jump of 10 and see what happens. Yeah, so you can see now these are the distributions. This is centered at minus 10, then this is centered at 0, then this is centered at 10. So changing the mu just shifts the distribution. Now let's fix the mu. Let's say let's fix the mu, for example, and play over sigma. Let's fix the mu and some mu. Let's say mu is let's say 2, and let's play with the sigma. Let's say sigmas is np dot range. Let's say the sigma is 1. The sigma can go to, let's say, 10. Let's say it takes a jump of 2, and see what happens. And now we loop our sigmas. So sigma in sigmas. So we just comment that up and see what happens if we just change the sigma, what kind of distributions that we get. So now you can see as the sigma, if you fix the mu, whatever the mu is, if you change the sigma, let's have the legend as well. Let's have the legend here, label to check which plot belongs to which, str sigma, and here we have plt dot legend, just to check what is happening. Yeah, so these are the sigma values. As you can see, smaller sigma, the graph is more peaky or sharp decaying, having a larger height. Larger sigma, on the other hand, as you can see, the graph is more wide and it changes smoothly. So sigma basically controls your decay rate, how faster it decays as you go far away from the mean. Smaller sigma means very sharp decay if you go far away from the mean or mu, and larger sigma means you decay very smoothly or slowly as you go away from mu. And mu is just where the graph or the peak is centered. So in this particular, if we set, for example, mu to be 0, all these will be centered at 0. So as you can see here, now all these, they are centered at 0. So changing mu shifts the distribution, but it stays Gaussian. Changing sigma just make the distribution more fat or more thin, but it stays Gaussian. So these two, mu and sigma, they are parameters of Gaussian. In NumPy there are methods to generate some Gaussian data or exponential data. There are functions. Let's generate, for example, and see the histograms. Let's generate some random numbers. Let's say x np dot random dot normal. You give the mean. Let's say mean is 0. Mu is 0. Sigma, let's say 1. And let's say I generate 1,000 points. Let's say that's x. Generate another Gaussian random variable. Let's say random dot normal. And we have, let's say, mu as 10. Sigma, let's say sigma as, again, sigma is large. And let's say we have 1,000 points. And let's generate another np dot random dot normal. Let's say mu is minus 10. It's centered at minus 10. The sigma is just, let's say, 4, and we generate 1,000 points. And we can also have yeah, so let's generate these, and let's plot the histogram of all these using so let's plot the histograms. So for example, plt dot hist, x density true, alpha value, just the see-through value, alpha equals, let's say 0.5, let's say that. That's a histogram. Different histograms. We can also have the density plots as well. But let's just go and plot the histograms and see how the histograms look like. So for example, yeah, so that's a Z, that is Y, and we can specify the number of bins as well if we want. Let's see what's the plot with default bins. Let's see what happens. Yeah, so you can see here. So we can also set certain. Yeah. So as you can see, when you have much more sigma, when the sigma value is much larger, let me increase the number of bins just to see what is happening in a bit more details. Bins equals, let's say 30. Here we have bins equals, let's say 30, and here we have, let's say bins equals 30, just to see what is happening maybe in a little bit more detail. Yeah, so that is what is happening. So this just goes like so, and that and that. These are three distributions, and not only that, we can generate an exponential distribution if we really like, and we can plot all these. So x, y, z, w, let's say np dot random dot exponential, and we can have scale, which is the inverse of sigma. Let's say scale is 1, and we can have, let's say, size equals, let's say 1,000 points, and we can also plot the histogram of that as well here, and that will look like more like that will look like exponential. So if you want to generate data from different distributions. So yeah, density true rather than Z, we have W here, and let's see what happens. Yeah. So yeah, the exponential distribution, that's the exponential distribution in this particular color that is not showing up. Let me just comment some of these and just show an exponential with one exponential and just one Gaussian. Let's see what that turns out to be. Yeah. So as you can see here, that's the Gaussian distribution centered at -10 with the sigma sigma 4, and that's the exponential distribution with a particular lambda, which is 1. Here the scale value is just 1 over lambda. So yeah, so you can generate a lot of data for normal random variables, for exponential random variables. You can generate, for example, you can have multiple plots for different distributions. You can have plots like this. So that's a normal random variable, that's a normal random variable, and this is what the exponential is. Actually, this random variable, the scale of this random variable is actually deteriorating everything. So let's just hide this and open up that just to see what happens. Yeah, so now you can see the histogram of normal, then normal, and then this is exponential. Yeah, so you can have, for example, distribution plots, KDE plots as well. But here the purpose just is to show you that once you know the parameters of any distribution, whether it is normal, it is exponential, it is a discrete geometric, it is discrete binomial, it's Bernoulli or whatever. Once you know the parameters of the distribution, you can generate a lot of data following that distribution. And once you have data, you can study more about the distribution, the histograms, the plots, and stuff like so. What normally happens is the reverse. We normally have a lot of data with us, and we somehow have to come up with with these parameters that actually are consistent with the distribution of the actual or the true distribution of the data at hand. For example, let's say we have a CSV file. Let us just see a let's see a real data. For example, let's say we have iris data. Iris is equal to sns dot load dataset iris. Let's say we have this data, and let's say x is simply iris dot sepal length. Let's say, yeah, so that's, let's say, our attribute x, and what we really do is we see hist of this x, density true, let's say, and we see what is the distribution of this particular attribute. Maybe we increase the number of bins, maybe to more, to see more fine-grained treatment. So yeah, so that's the distribution. As you can see, the distribution is no longer, it doesn't look like a Gaussian, it doesn't look like an exponential distribution. I mean, it doesn't look like the one that you already have seen. So the real situation is basically you're given data, you have a lot of attributes, a lot of random variables in the data. Assume in this case you have only one random variable. That's a continuous random variable. Histogram, if you see the histogram, that gives you a look and feel of the distribution, of the true distribution of the data. If you want to model that using some standard random variables that you have seen so far, this particular distribution, for example, doesn't look like any one of those. It doesn't look like Gaussian. It doesn't look like exponential. And maybe you come up with another random variable, very famous one, which this distribution may fit with, and then you model this distribution with that random variable. For example, if it happens to be a Gaussian distribution, it looks like Gaussian, it looks like a bell curve, then our next task will be to find out the mu and sigma for this data, to find out the true distribution that actually is generating this data. Because once having that distribution, then we can make a lot of predictions using that density function. So the exact procedure of finding out the distribution is really reversed. You don't have the parameters and then you find out the data. Actually, you have data and your goal is to find out the parameters or the true distribution that actually generates this data. Because once you have the distribution, then you can move on further. And sometimes the distribution may not be parametric. It may not be the one out of several famous distributions that you might be looking for. It may be something else. It may be something really different that you have never seen so far. It may not be even governed by a certain parametric function. It may not have parameters at all. And we will see those. There are methods to estimate the distributions, even if the distribution is non-parametric, sometimes called the kernel density estimates. We will see that there are ways to do that. But here we must notice that we don't have the distribution, because once we have distribution, we have a lot of things. We can move on towards predictions very, very quickly. But the reality is we don't have distributions. We have to model we have data, we have to model distributions. So given the data, come up with the distributions. Once you have the distributions, then you can answer regression and classification and a lot of other interesting questions. So yeah, and that part is basically deferred towards estimation in our next section, in which we will explain in detail from data how can we estimate the distributions. How can we, those distributions might be parametric, they may be one of the very famous distributions, or they may be non-parametric. For example, here in this particular case, if I just give you the class distributions for iris data, then it may look like to you something familiar. For example, if I just plot a pair plot, iris, and plot this using the categories as species. Now here you might be I mean, you might be astonished in seeing that several distributions, they may look like Gaussian to you. For example, if you see the distribution of Setosa, the distribution of sepal length for the category Setosa, that distribution looks, maybe it looks like a Gaussian, maybe, or maybe something else. Similarly, if you see the distribution of versicular, the distribution of sepal length, that's a random variable, sepal length. If you see the distribution of the sepal length in the real data for the category versicular, it looks like, much like, it looks like normal. Maybe not normal, but visually it looks like it is normal. Maybe that's a false assumption. Maybe there is another distribution, maybe a chi-square distribution or a beta distribution or a gamma distribution that models this particular curve better than a Gaussian distribution. But it looks like, now after visualization, I have some look and feel of what the individual distributions they look like for different categories. Here, for example, if you see the distribution, if you see the distribution of petal length, then the distribution of petal length for Setosa might be a very peaky Gaussian. Maybe it can be modeled with a Gaussian with very small sigma, and maybe the distribution of petal length for category versicular as well as the virginica, they both be modeled by Gaussians with roughly the same sigma, but with different mean, a shifted mean. Maybe we can model that. So yeah, I mean, and maybe these plots are completely different. I mean, they are not Gaussian, they are something else. At the end of the day, we have to find out these distributions. And not only that, right now we are focusing on distributions individually. What is the distribution of petal length given the category? What is the distribution of, for example, petal width given the category? We are not focusing, what's the joint distribution of petal length and petal width given the category? What is the distribution, how the distribution jointly, how petal length and petal width jointly distribute over the space of petal length and petal width when we talk about Setosa, for example, when we talk about virginica, how these petal length and petal width, they jointly vary, they jointly are distributed in what way? Yeah, that's a question. I mean, maybe the joint distribution is completely different. Maybe petal length and petal width, they are not independent. And the joint distribution is not just the multiplication of the individual densities. It may be something else. So yeah, we have to go a little far away to see the joint distributions. We have to see the data, we have to come up with the distributions, and then and only then we'll be able to make predictions which are required for machine learning tasks, for example, classification and regression. Yeah, so much more to come. Hope to see you in the next video. So in this video, we basically discussed Gaussian random variable, the very famous random variable, although it was just a single random variable. A more detailed treatment of the subject, probability and statistics, where we discussed multivariate Gaussian distributions, where we discussed joint distributions, multiple random variables, continuous and discrete and mixed random variables, Bayes classifiers, and a lot of stuff. For a more detailed treatment, I would recommend you to go to our website, AI Sciences, and just enroll our full course on that to see the detailed treatment of the subject. So yeah, hope to see you in the detailed course.